Alrighty, so we are doing problem plus number 9 out of chapter 14 in the book. And so with this problem, we have two equations. We have one ellipse that is represented by x squared over a squared plus y squared over b squared equals 1. And then we have one circle, x squared plus y squared is equal to 2y. So what we're trying to do is we're trying to enclose this circle in the ellipse, and we want to minimize the area between them. So kind of intuitively, the minimal area is going to be when the ellipse lies right on top of the circle, and that is this purple circle here, also an ellipse. So in order to solve this, we're going to set up a system of equations. We're going to change this format so that we have an x squared equals, and change this format so that we have an x squared equals as well. So this one's real simple, just move over the y squared. This one's a little bit more complicated. Move over this section, put in a b squared over b squared for your y, and then multiply your a in on top. Factor that out for the time being. Then, with this system, we can set them equal to each other because x squared is in fact equal to x squared. So 2y minus y squared is also equal to a squared over b squared times b squared minus y squared. From there we have an equation that's just going to end up working better for us in the long run. It's a simplified version, and this is the basic form. From there we know that if we only want one solution to this, we're going to have to set our delta equal to 0.
So at this point, where Kaysen left off, we just know that our delta is equal to 0. And this is demonstrated by this equation here. And in this particular case, a and b are both constants because delta is 0, and so y is our only thing that's changing. And so we can treat this sort of as a quadratic, and because delta is equal to 0, delta is equal to b squared minus 4ac. And so we put that into place here. Our b squared minus a squared over b squared is our a in this case, and then our negative 2 is our b, and our a squared is our c. And so using that, we get 4 minus 4a squared times b squared minus a squared over b squared, and then that just simplifies to b squared minus a squared times b squared plus a squared is equal to 0. Now, this would be good, except we still have two unknowns, b and a, but luckily we are trying to minimize our area of our ellipse, and so if we use this as a constraint function, then we know that if we could take basically the gradient of our area, that's going to be equal to lambda times del g, and then we'll be able to make an additional system set of equations and solve for both a and b using them.
So we left here, so we're going to use Lagrange multiplier in order to solve this equation and figure out the values of both a and b. Our objective formula here is going to be our delta, so we can just say that g is actually our delta equal to 0. So at this point, all we have to do is figure out the gradient of both our area of the ellipse, which is given by pi ab, and our delta. And we have to consider the gradient, so the prime derivative, both for a and b. So here I just estimated the partial derivative with respect to a, and I got pi b equals lambda that multiplies the derivative with respect to a of our delta equals to 0, so it's going to be 4a to the third minus 2ab squared. I did the same thing with respect to b, and finally, as my third equation to solve this system, so that we have a system of 3 equations and 3 unknowns, I just used our initial equation, our objective equation. So, and that's just equal to 0 now. Of course, we can't solve it like that, so I've reorganized everything, and I wrote those two in terms of lambda so that it's easier to solve this system. And once you solve it, you end up with a equals the square root of 3/2. That can be rationalized into square root of 6 over 2. And b is just going to be b equal to 3 over square root of 2. That is just equal to 3/2 square root of 2. Thank you for watching.